Good morning, everyone. In today's class, we will be discussing Unit 1, Module 2, Lecture 3 for the course PH 8151 Engineering Physics. In today's lecture, we will be explaining how the projection of uniform circular motion on any one of the diameter is simple harmonic. And we will also be discussing university exam questions and problems pertaining to Unit 1, Module 2. So, we have seen that a torsional pendulum is an angular harmonic oscillator. It has a wire of length L, radius R, and rigidity modulus eta. And when an external torque is applied to this disc, the disc gets twisted by an angle theta. So, there is a corresponding twist at the end of the wire theta, which results in development of restoring torque C theta. Here C is couple per unit twist, which depends on the characteristics of the wire. It is given as pi eta r power 4 by 2L. So comparing this expression of applied torque equal to restoring torque, we get alpha, the angular acceleration, is proportional to the angular displacement, theta. Let us compare this with the condition for simple harmonic motion. A equal to minus omega naught square x, where omega naught is the natural frequency of the simple harmonic oscillator. So, T equal to 2 pi by omega naught. Here comparing this expression with the condition for SHM, you have omega naught equal to root of C by I in case of a torsional pendulum. This implies the time period T is 2 pi root of I by C. So what is the basis on which we get the time period T equal to 2 pi by omega naught? Let us analyze it based on our consideration of uniform circular motion. When I say uniform circular motion, I have a bead that is moving with a constant angular velocity in a circular path. The angular velocity of the bead is omega naught. Let this be the x-axis with the origin fixed at the center of the circle. At any time t, let the bead have traversed an angle theta. Let xm be the radius of the circle. So, the position vector is of length xm, but its direction changes as the bead moves. So, at time t, let this be the position, new position of the bead. So, we have the initial conditions at time t equal to 0, theta is 0 and x is given as xm. Okay, the x coordinate of the projection is given as xm. Okay, so at the new Now, at this new position at time t, the projection at this new position at time t, the projection on x-axis is given by the x coordinate. Okay. So now here at time t, adjacent side is x and hypotenuse is xm. So x by xm is cos theta, but theta is omega not t, because the bead is moving with a constant angular velocity omega. The angle theta will be equal to omega naught t at any time t. At any t, theta will be omega naught t, and from this expression you have x equal to xm cos omega naught t. Okay. When the bead has traversed a complete rotation, that is when it has fully made an angle 2 pi, the time taken for one complete rotation, let it be capital T. So T omega naught T would be equal to 2 pi, which implies the time period T is 2 pi by omega naught. Okay. So suppose if you consider the bead has moved to this position, then the corresponding x coordinate would be 0. So let us analyze it mathematically. When t equal to t by 4, that is 1 by 4 of the time taken for one complete rotation, then theta would be omega naught t by 4, but omega naught t is 2 pi. So substituting that value here, you will get theta as pi by 2. Okay. So corresponding x value would be xm cos pi by 2. Corresponding x value would be xm cos pi by 2. So x would be 0. At t equal to t by 2, that is, the bead has completed half rotation at t equal to t by 2. This is at t equal to t by 4, where it has completed 1/4 of the rotation. At t equal to t by 2, the bead would have completed half rotation. So the corresponding x value would be minus xm. Physically, we can observe that it's just, since this is the positive x direction, this is plus xm, whereas this position is minus xm. Okay. So theta would be, but mathematically also we have the proof, theta would be omega naught t by 2, but omega naught t is 2 pi, so theta would be pi. Cos pi is minus 1, so you have x equal to minus xm. Similarly, when the bead completes 3 by 4th the rotation, comes to this position, t equal to 3 by 4 t. So you have theta equal to omega naught 3t by 4. So it becomes 3 pi by 2, that is 270 degree. The corresponding x value would be 0, which is also evident from this projection. Okay, x value would be 0. At t equal to capital T itself, you will have theta to be equal to 2 pi and x to be equal to xm, same as the initial condition, same as t equal to 0. So here on, for all t equal to nt plus t is same as that of t itself. Any time. So this is called a periodic motion. This is evident the projection of the uniform circular motion is a periodic function because at t equal to 0, it is at the positive, at t equal to 0, it is at positive xm. It becomes 0 at t equal to t by 4. It becomes negative xm at t equal to t by 2. Again becomes 0 at t equal to 3t by 4. And the periodic motion continues like this. So starting from the left extreme, the projection of the bead continues to oscillate like this. So it is to and fro motion. And in addition, since x is xm cos omega naught t, dx by dt would be minus omega naught xm sine omega naught t, whereas d square x by dt square would be minus omega naught square x itself, because xm cos omega naught t would repeat, which is x. So you have acceleration equal to minus omega naught square x. So going back to the slide here, you have the condition for simple harmonic motion to be acceleration equal to minus omega naught square x. That is what you have here also. That's why the projection of uniform circular motion on any one of the diameter. So we have the statement, projection of uniform circular motion on any one of the diameter is simple harmonic motion. Okay. So this was first proposed by Galileo, the famous scientist Galileo. He observed one of the moons of Jupiter. So this is Jupiter. He observed a moon of Jupiter called Callisto. He plotted the position of Callisto. He was observing the moon of Jupiter from a very large distance from Earth. So he plotted the position of Callisto with respect to time, and he proposed that the projection of uniform circular motion, because Callisto is a moon that revolves around Jupiter at a constant angular speed, omega naught. So the projection of uniform circular motion on any diameter is simple harmonic. That is, it obeys the condition that it is to and fro along a straight line, and that the acceleration is proportional to displacement and directed opposite to it. Here, omega naught, the angular frequency of the corresponding uniform circular motion, is called the natural frequency of a simple harmonic. And the time period of the simple harmonic oscillator is given by 2 pi by omega naught. Okay, this is how uniform circular motion and simple harmonic motion are related. Now, let us discuss this question which has come in one of the university exams. A torsional pendulum is made of a steel wire of diameter 5 mm. So, you have a torsion pendulum made of a steel wire whose diameter is given to be 0.5 mm. Instead of a disc, you have a sphere attached to the end of this torsion pendulum. The sphere has a diameter of 3 centimeter. The density of steel is 11,300 kilogram per meter cube. So the mass of the sphere would be density times the volume, that is density times 4 by 3 pi r cube, where r is d by 2, that is 1.5 centimeter. Okay, so you can find the mass, and the moment of inertia of a sphere about its axis would be 2 by 5 m r square. So r is known, mass can be found using this formula. You can calculate the moment of inertia here. Now, the time period of oscillation is given to be 2 seconds. But we have time period as 2 pi root of I by C. I is known, so you can find what is C. Theoretically, we have C is pi eta r power 4 by 2L, where eta is rigidity modulus of the material of the wire, r is radius of the wire, L is length of the wire. So the length of the wire is unknown. You have to find what is the length of the wire. You are given that the rigidity modulus of the wire is 80 giga. Giga is 10 power 9. 80 into 10 power 9 Newton per meter square. And you can find the radius of the wire using the diameter. Diameter by 2 gives you the radius of the wire. So the couple per unit twist, that is the torque required to twist the wire by 1 radian, can be computed from the known quantities. So by computing all this, you can find what is the length. Okay. So do the calculation and come up with the answer. So wire of length 1 meter and diameter 1 mm thickness. This is another question that has come in one of the university exam question paper. A wire of length 1 meter and diameter 1 mm. So radius is d by 2. You can find the radius. Is fixed at one end. The rigidity modulus eta is given as 298 gigapascal. That is 298 into 10 power 9 Newton per meter square. What is the couple required to twist it at the other end? What is the couple required to twist the other end by 90 degree? First, you calculate the couple per unit twist. Couple per unit twist is given as pi eta r power 4 by 2L. All these quantities are known, so you can compute the value of C. The torque or the couple required to twist the other end of the wire by 90 degree, that is pi by 2 radian. Okay, 90 degrees pi by 2 radian would be C into d theta integral 0 to pi by 2. C is a constant, you can take it outside. On integrating d theta, you have theta, and applying the limits, you get C into pi by 2. Okay, so you have to compute the value of C and multiply it by pi by 2 to arrive at the couple required to twist the other end of the wire by 90 degree. Okay, so we can do this also as homework and come up with the answer. This is one of the 16-mark question that has been asked repetitively in the university exam question paper. Derive an expression for rigidity modulus of the material of the wire. So in order to derive an expression for rigidity modulus, you have to first derive that C is pi eta r power 4 by 2L. Then by using the principle of simple harmonic motion, you have to show that T equal to 2 pi root of I by C. In substituting for C and simplifying this expression, you would have eta equal to 8 pi IL by T square r power 4. Okay. So arriving at this expression would fetch you 12 marks. Then you have to explain how you will find the time period of a torsion pendulum. Then you have to explain how will you measure the length and radius of the wire, and also how you will compute the moment of inertia of the disc, and using it to compute the rigidity modulus of the material of the wire. In today's class, we have discussed how the projection of uniform circular motion on any one of its diameter is simple harmonic. We have also discussed the university exam questions and problems pertaining to Unit 1, Module 2, that is the torsion theory, torsional stresses, torsion pendulum, and how the torsional pendulum is a angular harmonic oscillator. If there are any queries, you can address it now.